Let us go for the next problem, which is problem number 4. It doesn't involve any new concept, but it's more challenging because the problem is innovative. Problem number 4 is telling us, for the arrangement shown, find the time interval after which water jet stops crossing the wall. Cross-sectional area of container is 0.4 meters square and cross-sectional area of the hole is 2 centimeters square. And here is the figure given. A container containing water initially is totally filled up, and the height of the free surface above the hole, that is called capital H. This H is given to be 0.75 meter. Also the cross section of the container A1, that is given to be 0.4 meters square, and the cross section of the hole, which will be taken to be A2. This cross section A2 is given to be 2 centimeters square, that is 2 into 10 to the power minus 4 meters square. It is further given in the figure, as the liquid jet is coming out of this hole, there is a wall at a distance from this hole. Let's locate this first. The wall strip is located at a distance of 1 meter on the right side of the hole. This distance is 1 meter, and at a depth of 1 meter below the hole. So this length is also 1 meter, and here stands the tip of this wall. You see that initially when the height of liquid is quite large, the efflux speed is also large enough, and the liquid jet can have a large range so that it can cross the wall. But as the height of liquid comes down, the speed of efflux decreases. These water jets range decreases, and eventually at a point it just fails to cross the wall. You have to find out after what interval, since water starts coming out through the hole, this happens. That is the time after which the water jet stops crossing the wall. That is the question here. So once we understand the problem, let us consider an intermediate situation. It was the initial situation, the height was h above the hole, but we will now consider an intermediate step where the liquid level has come down, and let us suppose this variable height of the liquid's free surface above this hole is small h at a given instant, right? The value of the speed of liquid inside the container is small enough. You know the Torricellian theorem that tells that the speed of a flux as it comes out of the hole, I used the symbol V2 for it earlier, and V1 for the speed of liquid at the free surface within the container. So we have already seen earlier that V2 can be approximated to be square root of 2gh, where h is the height of free surface above the hole, and since the container's cross section is much larger than the cross section of the hole, the speed V1 is much less than V2, and therefore we might ignore V1 compared to V2 and get to this result. That is Torricellian theorem. So this V2 is a function of h. As h comes down, V2 comes down, and the range of liquid also comes down. So our first job will be to find out at what minimum value of this h the water jet fails to cross the wall. That is the first step of the problem. And to do this, we shall choose a coordinate system whose x-axis is pointing horizontally to the right, y-axis is pointing vertically downwards. And the origin of this coordinate system is taken at the mouth of the hole. That is the origin whose x and y coordinates are both 0. Therefore, you understand, during the flight of this liquid jet coming out, this V2, the speed of efflux, becomes the x component of initial velocity vector during the flight, while the y component of the initial velocity vector is 0 because the liquid comes out horizontally with no vertical component of initial velocity. And the only acceleration acting on the liquid during its free fall in this parabolic trajectory of a projectile This is a free fall acceleration g acting vertically downwards. So therefore, for the x motion, we might write down x motion means the motion of liquid in the horizontal direction. The x coordinate of the liquid element coming out of the hole, that is given by ux into t plus half into ax into t square, where ux is the x component of initial velocity and ax is the x component of the acceleration. We know that with a vertical acceleration of g, this ax is equal to 0, and therefore x coordinate of the liquid, let me take any point here and I take this point's coordinate is x comma y. We are trying to find out this x and y as functions of time of flight. I mean how long it is falling, that is t. This is ux value, this is equal to v2 only, the speed of a flux, and into the time of motion during the flight, ax of course is 0, and therefore I have got my next term is equal to 0, and I get that x coordinate is given by speed of a flux v2 into t. Next we consider the y motion of the liquid during the flight, and the y coordinate is given by uy into t plus half ay into t square. Initially there is no y component of velocity, so this term goes off. Acceleration ay is equal to plus g according to my sign convention, downward taken to the positive direction, half gt square. So we are getting that the y coordinate of the liquid element as a function of time is half gt square. We'll eliminate t between the two equations and express and get the equation of this trajectory of the liquid element during the flight. Let's do that next.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.